Okay, we have one more kind of projectile to analyze, and those are elevated projectiles. These are probably one of the tougher ones for students to get used to. This is where you're standing on a platform that is higher than, say, where the actual projectile will land. Okay, so a lot of things we've done up till now have been either off of ground level, returning to ground level, so you get this nice parabola that's symmetrical on both sides, or we've done things that go straight up or straight across. But here we have an angled projectile that's launched off of an elevated space, okay, an elevated place compared to where it's going to land. Now, when you look at this, there's lots of ways to do things. So we've talked about how there's multiple approaches, and I like to try to give ways that students maybe haven't thought of yet, or sometimes just a way that I see, even if it's not the quickest way, it maybe makes the most sense. So when I look at this, I could try to treat this problem like this piece doesn't exist. And I could just calculate and figure out all the physics of this little parabola here. But then I'm left with trying to add this piece on. That's definitely doable, but sometimes the math in that gets a little messy and it just turns into kind of a headache. So I choose to look at the problem like this. I'm gonna deal with what's happening as we go up and then what's happening as we go down. And those two pieces put together will tell me what's happening horizontally, okay? I'm going to try to color code this as much as possible, but that's how I'm going to approach this problem. Now, I just picked this projectile leaving at 17 meters per second with initial velocity angled at 40 degrees from the horizontal. So I'm going to write that triangle over here, and let's just make sure we do our trig correctly. This one, the vertical, is going to be 17 times sine of 40. And the horizontal is going to be 17 times cosine of 40. Now, I've got these pre-done, so I don't have to calculate it at the time. I'm going to end up with a horizontal of 13 and a vertical of 10.9. 10.9 meters per second, and a horizontal of 13 meters per second. Remember, once we do that, we are no longer going to pay attention to 17. It doesn't represent anything we need to look at because we're going to look at these vectors independently. All right, now I kind of outlined for you sort of the way I approach this, and this is just one way of doing it. Once again, some of you will find shortcuts or avenues where it gets you to the same spot. Go for it, all right? This is just how I like to kind of break it down mentally. I'm going to pay attention to what's going on just on the way up, okay? So this half over here, from the platform till it gets to the top of its arc. So I'm going to analyze what's what's happening on the way up. Then I'm going to analyze what's happening on the way down. And when I'm done, what I'd like to find is the amount of time it takes to get here and the amount of time it takes to get here. Remember, my sketch is not proportional, but we should at least get some numbers that seem like they could fit. Okay? So let's start with the way up. All right? On the way up, I know that it leaves with an initial velocity in the vertical direction of 10.9 meters per second. I know that as it leaves this platform, as soon as it leaves the platform, gravity is going to start pulling it towards Earth. Okay, so it's going to start slowing it down at a rate of negative 9.8 meters per second squared. The final velocity, once it gets up here, that final velocity in the vertical direction, not the horizontal, vertical direction, is going to be 0. I'd like to know how long it takes for that to happen. Okay, and eventually I'm going to figure out how high it goes as well. That part you'll see is probably not proportional to my drawing, but I had to space the drawing out and stretch it enough so that I could write things in. So the first thing I'm going to do is figure out time. I'm going to use, let's see, how about final velocity equals initial velocity, plus AT. Now keep in mind, in this case, the gravity acceleration is slowing this down until it gets to the top, so I'm going to make it negative. So I've got final velocity is 0, initial velocity 10.9 minus 9.8t. It's plus negative, so I just made it minus. When I solve that, I'm going to end up subtracting 10.9 over here and then dividing by negative 9.8. I end up with a positive numbers for time still, which I should. Okay, and in this case, I calculated this and time should be 1.11 seconds. Now remember, we didn't find everything here. That means to get to the top of this, it takes 1.11 seconds. Okay? So it gets to the very top of its curve and then it starts back down. So there's a moment in time where it's actually not moving up and not moving down. That's the spot we're analyzing. 1.11 seconds. Okay, now before I go any further, I'm also going to find out how high it went. So I need to figure out this displacement. All right? I know it started at 20 meters, and there, like I said, there's more than one way to do this, but I'm going to pretend this started right at the ground level. I'm going to ignore this 20 meters and just figure out if I launched it from ground level, how high would it get with those parameters right there. Okay, so I'm going to do final velocity. So which one did I use? You know what? I used a different one there, and really there's more than one way to do this, but I'll go ahead and use this one just because we kind of avoid it sometimes. All right, so if we do the x final equals x initial, and in this case I'm just going to say x initial is 0. I could say it's 20, but I'm trying to simplify the math. I'm going to pretend I'm at ground level and then I'll interpret the results. My initial velocity going up is 10.9. And that happens for 1.11 seconds. Okay, I'm not going to include the units right here. And then I have 1/2 AT squared, 1/2 negative 9.8, and then T squared would be 1.11 squared. Now when you punch that in and compute that, you're going to find that this thing goes final distance of 6.06 meters. Now let's remember what we just did here. I assume that was ground level. What it means is this is 6.06 meters. So if we label things as we go, we will be less likely to make mistakes on misinterpreting things. I pretty much figured out everything there is to know about the upward part of this path. Now I need to switch and do the downward part. Okay. However, think about this I don't know, in a bigger sense. I know we're launching something like this, but once you get to the top, we could almost treat this like this part of the entire problem doesn't exist, and this is just in free fall. We're not worried about the horizontal yet, so it's like it's starting from 0 and it's just dropped. Like if you were just to drop a rock from this height and had to go to the ground, that's the same as what we have here. We just ignored the first half. So I'm going to treat it like this is a free fall situation, because it is. At least in the vertical sense. Okay, it's just free fall. From a height of 20 plus another 6.06. 26.06 meters high. Okay, so that's the little adjustment we have to make. So if I list what's going on now, at this very top of the arc, its initial velocity now is going to be 0 because it's like starting from just free fall, like there's just drop. My final velocity, I don't know, but my acceleration now, once it starts from here on the way down, gravity is definitely speeding it up towards Earth. For the purposes of making this simple, we're going to make that a positive 9.8 meters per second squared. And then the distance that it's going to drop, the final displacement, if you want to treat it that way, it's going to be 26.06 meters. Now if I look at this, I do have a time, well, time is kind of where I'm trying to get to, but I got to figure out one of these equations that's going to help me, okay? Which one of these is going to kind of get me where I need to go? Eventually, I'd like to know how long it takes to get from here to here. So what I'm going to do is I'm going to go back and use this equation, but now I'm going to interpret it from the second half of this trajectory, of this path. So x final equals x initial plus initial velocity times time plus 1/2 AT squared. Now, if we interpret this based on what we see, it has to eventually travel 26.06 meters. But we're going to say its initial height here is 0. If this is 26.06, then this has got to be 0. Or we can make this 26.06 and this 0, and then we get a bunch of negatives. So I'm just going to try it this way. My initial position is 0. My initial velocity is also 0, so that entire term disappears. That's the nice part about this formula. Sometimes you get rid of some terms and you don't have to deal with it. Now, I got 1/2 AT squared left. 1/2 times positive 9.8, because it's speeding it up, times t squared. I just need to solve that for t. So I need to basically multiply those together to get 4.9. I'm going to divide 4.9 over to this side. That's the algebra. And then I take the square root to get t by itself. And when I do that, I get a time, 2.3 seconds. That's this part right here. So from here all the way to here, 2.3 seconds. I know how far it dropped, 26 meters. I know it took 2.3 seconds to do it. Kind of makes sense. It's only going up 6 meters. It's going to take barely over a second. This is going to take almost 2.5 seconds because it's going a lot further down on the other side. Okay, so I've got a lot of stuff figured out. The important things, though, are this and this. Okay. Why did I find that? Because I needed it to get the other chunk that shows me the time. But these two things put together give me my total time that this is in the air. And that's what I want for the horizontal. I need to know how long it's in the air, traveling at a constant speed of 13 meters per second in the horizontal direction. So I'm going to add those things together, and I get a total time of 2.3 plus 1.11, that's 3.41 seconds. So the entire time of flight is 3.41 seconds. I know my velocity in the horizontal direction never changes. We're ignoring air resistance, so it's not going to change. 13 meters per second. So the distance that this is going to travel, basically we're trying to figure out this right here. How far away from that building or that platform does this projectile hit? That's going to be velocity times time. I just have to multiply those together. The math's real easy. When I multiply them together, I get 44.33 meters. So this lands 44.33 meters from the base of that building. That's pretty much everything there is to figure out about that elevated projectile. The process will be the same. Now, it's not the only way to do it, but it's how I like students to break it down, because if you can do this, there really isn't any physics you can't do with projectiles. Like, you know everything there is to know about that particular situation. And that's how you approach an elevated projectile.